We'll get started. So today's speaker is Robin Hanson, who is coming from George Mason, and he's going to talk about uncommon priors require origin disputes. Thank you.
Feel free to ask questions and comments, and I'll feel free to say that'll be a little better later. All right. So, as many of you may know, in economics, which is my profession as a professor of economics, there is a standard way that we model agents, which is we model Bayesian agents of a particular sort. It differs perhaps somewhat from models elsewhere, but as far as I can tell, it's pretty similar in a wide range of places. So our standard model has a large state space, as large as necessary, so that each state resolves all the relevant uncertainty. Every question you have is answered in each state. Every agent has a prior, which is a probability distribution over this largest possible state. And in particular, it's the one thing this agent uses to produce all their beliefs at all times and in all situations. And so your beliefs only through the standard expected conditional expectation that you estimate any random variable using your prior by conditioning on your information set. And so therefore the information set contains everything you need to know about what people think. Prior. People have an expected. Make the choices to maximize expected utility, which is this random variable across the whole state space. And we also very commonly assume a common prior, that is, all of the different agents in our models and our analysis have the same prior. Not only is it the same for any one agent in every time, in every case, it's the same for all agents in all cases and times. In modeling agent actions, one can make the observation that differing prior is equivalent to just a different utility function. So if you're going to bother to have a different prior, why not encode it in the utility function? Just leave it like in one place instead of two places. But of course, in addition to doing expected utility, we have some statistical concepts of beliefs, whereby beliefs are not just something we use to produce expected utility things, but we also have beliefs about the chances of seeing something, and that's an independent concept, in which case the common prior is a stronger assumption than merely a way to represent arbitrary utilities. All right, so that's the standard economics framework whereby we model things. I'm going to go over this in a lot more detail, but I'm trying to motivate here. One of the things that I spent a lot of time doing is exploring a literature, welcome, on the rationality of disagreement, which Robert Aumann won a Nobel Prize in the 2000s for his work. His most cited paper was a paper on We Can't Agree to Disagree, published in 1976. This is where he introduced much of the standard framework that economists now use, or at least important additions to it. And he proved basically that two agents would not disagree with a number of strong assumptions. And so I'll quickly mention those strong assumptions. And the key thing to notice is that over time, people have worked to weaken these assumptions. And so today we have a much stronger result in the sense that much weaker assumptions still seem to produce the result that the agents would not disagree, or not knowingly disagree. So Aumann started with any finite information structures. The agents could have arbitrarily developed information. Initially, of course, this was about possible worlds. He assumed that two agents had common knowledge of the exact values that each of them have for the expectation of some random variable. And that this is, of course, of what they would say there. So this isn't what they said last time or believed at some previous point. This is common knowledge of what they currently believe, and therefore of what they would say next, and that they were Bayesians, according to the structure that I just described, and that they had common priors, which implicitly says they're being honest, basically. So these are relatively strong assumptions, which have, of course, been criticized for being irrelevant for real disagreement, because real people don't satisfy all these assumptions. And since then, people have generalized these things to various kinds of infinite spaces, to impossible worlds, not just possible worlds. This strong, very strong assumption of common knowledge has been weakened to something called common belief, which is vastly more plausible in most human situations, but it still gives nearly the same results. instead of knowing the exact two values two people would have, it's sufficient to know who has the maximum value or any monotonic function of those two. Instead of knowing what they would say next, it's sufficient to know, have a common knowledge of what one of them said last about the sign of one difference, which is the difference between what one person thinks and what they think the other person will think at some future point. So merely common knowledge of that signed difference is by itself enough to produce no disagreement, i.e. this having.
So they start out not disagreeing because they have common priors, right?
Well, this structure has no time in it, except at the moment we're introducing a time here. But before that, we didn't have any time, so it's just at any time, at any point in time, if these assumptions are satisfied, then they do not disagree. They agree. And so here we're introducing this idea of this expectation of
maybe I
future.
don't understand something about what. So if they have common priors, doesn't that mean that they assign the same credences to all the propositions they entertain?
So as we said before, their beliefs are based on an expectation given their information sets. So here they quite definitely can have different information sets. So with different information sets, they could in principle have different beliefs. So they have the same prior, and they may have the same definition of random variables or even the same utility, but they have different information. That's the key point. And here we started out with any arbitrarily different information. So not just any kind of information, but each of them can have different information, and arbitrarily different information. And all of these theorems are in the context of arbitrarily different information. And then
so when you say they have common priors, I understood that as they all have exactly the same credences, but they don't because
no,
they
do
have
not.
different information.
So
what does common priors mean?
Well, I was going to say this on the next slide, and I will. So let me just pause for a moment to get to the next slide. But the key point is we keep generalizing it here. We generalize Bayesians to various kinds of logical agents who are like Bayesians. One I'm not called Bayesian wannabes. There's a lot of ways to generalize Bayesians that still give these results. And all these results are depending on the common prior. And the main thing I'm going to talk about today is a result to generalize from the common prior assumption to something that's apparently weaker that still gives you as strong a result as you need to get common priors. So that's where this sits in my previous research agenda. This is what I'm telling you, is that I was focused on the rationality of disagreement and generalizing these things, and this seemed to be the nut that most people would say, sure, you can generalize other things, but common priors, you need that, don't you? And I'm just going to deny that. And so this is about showing that common priors are a weaker assumption than you might have thought.
I wanted to know what it meant in Hellman's theory.
So
what they mean by
a prior is, so the key thing is you just have this largest set of possible states. All the states you could imagine that anybody might imagine might be true. The largest a prior is a probability distribution over that large set of states. And that's literally what it means. So it's in a sense, your counterfactual belief, if you knew the least imaginable. A prior is literally in the standard model that. It's the beliefs, your credences or beliefs in the counterfactual situation where you know, we unknow everything it's possible to unlearn or unknow. And then we reproduce every particular belief by adding information back in. So we sort of,
and different people may have different information.
right, and different people have different information. Well, then produce different beliefs. Exactly. And so that's the whole idea of this conditional expectation here. It's the differing information that produces the differing expectations. The prior stays the same for all time and all possible cases for this person. And if it's different people, with the common prior, it's the same prior for all of them. They will then have different expectations because they have differing information. That's the key idea. So it's the Bayesian framework is usually trying to attribute almost all chain differences in beliefs across time, across cases, across people to differing informations. That's the ambition of the project. And the key question is it sufficient to attribute these differences to differing information, or are there other fundamental differences that need to be taken into account in explaining beliefs or credences? And that's the key Bayesian point in a sense. So, in this slide, the point is that one way to think about priors, one face of priors, is this role in these models as the thing that drives all the rest of the beliefs from the uber counterfactual belief, the one thing you would believe if you knew nothing, or the least imaginable. But another face of priors is that if we think of priors as something we're using to model people and their behavior, and we're considering that, for example, that they might have differing priors, then priors are a feature of people for which we can think about the causal origins, the correlations. We can say, where did those priors come from? What caused those priors? That's another face of priors, and we might hope to use that as a constraint on priors. That is, we might say, in principle, all possible priors are acceptable within this framework, but if we're going to have a normative framework, an epistemic framework, say not all priors are equally or acceptably valid. Some priors are reasonable and some not. And we might hope to use these beliefs about the causal origins of priors as a way to constrain which priors are reasonable. And that could give us some purchase on this question of what are the reasonable priors, or where do you get a prior, that sort of thing. And so that's the structure of this paper, is to try to get a result like that. And the key thing to notice that a problem we're going to solve is, within this standard structure, as I'll repeat showing you, priors themselves are always common knowledge. We always know that we know that we know arbitrarily everybody's priors. That is an obstacle to reasoning about the causal origins of priors. As you know, when we reason about things, we usually reason about events which are not universal events, so that we can have different probabilities for different events, and we can talk about conditional probabilities and correlations and independence, etc. But how do we do that? How do we reason about that for priors if priors are always common knowledge and always fully known by everybody? So I'm going to pick a theoretical trick to get around that problem, and that'll be the key contribution to this paper, and then I'll give you some results from it. And that's the whole trick here. So, but to think about it, to say origins of priors, so let's say you think of yourself as a creature who can be represented as a Bayesian with priors, and your priors are somewhere in your brain. There's a section somewhere that represents those priors, and you know that, and you watch somebody go in with tweezers or electrical stimulation or something, and they go change your prior. And they take out the tweezer, and now your question is that okay with you? Was it okay for them to just go in and randomly change your prior? Are you just as equally embracing the new prior as the old one? And I'd say most people think, well, no, if I liked my previous prior, I don't think arbitrary random changes in my prior are things I want to embrace. That would be not rational or epistemically useful to just go in and make random changes, right? Other things, if we think your prior is either encoded in your genes or your culture, we have a lot of theories about how these things are produced. We have, say, theories of how the different siblings of the same parents have their genes produced through various random processes, and that produces beliefs about the correlations and independence of the various features of children, and those could be constraints on beliefs about priors. If the beliefs are encodes in genes, then their statistical properties would have to follow our beliefs about the statistical property of genes. And we'll actually be making use of something like that. So the point is, in principle, we have beliefs about priors, and priors are something inside people that produces their representation as a Bayesian, then that arose through some process, and that can be reasoned about. That's the whole game here, is to try to reason about that, all right? So to hint the future result, but many of these theories we have about the origins of our structures, our cultural structures, our genetic structures, have us individually not being special. They say that you or your brother are, from some prior point of view, equal. And you should find a symmetric way to describe how your features were generated and how their features were generated. But I will show that having uncommon priors requires you to reject that, to believe that you are special in certain key ways. And that will be the main way in which I reject uncommon priors, is to say they require beliefs in the specialness of the causal origins.
So a person with priors is committed to those being the right priors.
Well, in essence, if you are committed to your beliefs of any sort, and they are represented by your priors, then the priors is a representation of all your
One
beliefs.
of the things that the trouble here is, from the very beginning, that representing ignorance shouldn't be with priors at all. This is because you're doing it because you're doing this as Bayesian
Well,
modeling.
there's two parts. I mean, in the Bayesian framework, just to give it its due, it says there's two parts that produces your credence. One is your prior, and the other is your information. So it will try to represent as much as possible about your ignorance in the information part of your ignorance, but it claims that there's this residual part in order to produce your beliefs. It's not enough to know your information. We also need this other thing, which is your prior. And the claim is you can't do without this
Right,
other
and the
thing.
trouble is that some people look at that and they say, no, if you're really ignorant, you shouldn't have any priors.
Well, then they might say you shouldn't have any beliefs.
No,
So-
that doesn't follow.
Well, here we're representing the beliefs as if the Bayesians have beliefs, then the Bayesians' beliefs are representable by a prior.
Yeah, so this is a commitment of Bayesianism, but this is an objection that some people make to Bayesianism.
And maybe we could explore that But let's first see what happens to Bayesians, because Bayesian is a really common structure and a common way to represent. And this is a common thorn in the side of Bayesians for a long time, which is the arbitrariness of the priors or the arbitrariness of common priors. So at least here we're trying to have a solid argument for common priors. And that's the whole game that we're trying to play here. But yes, of course, to grant, Bayesian framework itself is not obviously the right one. Obviously best. This is all assuming the Bayesian framework and see what we can do with it. But it is a very common framework. It's very useful in many cases. It has many advantages, so it might be worth seeing what the framework can say. All right, so we're just starting out with a very simple example. So I gave you the abstract terms, but here are 4 states. And there's one random variable, x, and in this state x is 1, 2, 3, and 4. 4 states, 4 values of x. There are 2 variables we can think about, each a binary, an A and a not A, a B and a not A, and so you can use that to lay out the 4 states. And we're going to have 2 agents, and they can even have differing priors here. So this person has a 1/4, 1/4, 1/4, 1/4 prior. This other red person, P, has that, and the Q red prior has 1/3, 1/3, 1/6, 1/6. So this just represents a simple standard model, i.e. a set of states, a random variable, at least one, over these states, more than one agent, each of whom can have different priors in the general case. And so this is the idea of a standard model. We can then add information. We can say, let's say that Q knows B, whether B is true or not, and P knows A, whether A is true or not. Well, then we will look at the A's beliefs. When they know that A is true, then they will condition on that and average over these 2 states to get an expected value of x of 2. They know that not A is true, they will average over these 2 states, expected value of 3. And similarly, B will then average over these 2 states when they know B, and when they know not B, they'll average over these 2. This is just the description of the standard model for the purpose of particular agents, making particular expected values. This is the general idea that we produce the beliefs of any one agent in any one state according to their information involved with their general prior.
So information here doesn't mean true information. It's just...
Well, it is true information here in this model.
I thought you just said that whether it's true or not.
There's the truth of whether B is true, and there's the truth of whether B is not true.
Right.
And in each case, if Q knows that not B is true, it is in fact not true. B is not true. And then they are in this state. And so this information they have that they're in one of these 2 states is true information. They are in fact in one of those 2 states. It's not full information. They don't know exactly which state they're in. But it's true information. It's reliable. They know that they are in that set. So an agent has an information set. In this case, the information sets are these 2 and those 2 for one agent, and from the other agent, it's these 2 sets, those 2, and those 2 are the other information set. So this is a very simple case of a space state of a set of states, some agents, information for each agent, random variable, and how that produces their final expectations. That's the whole point. To go through it in great detail, just have a very concrete example here. And now, I'm going to say, I'm going to embed this model in a larger, more extended model, which is the trick I'm going to use to be able to talk about priors and their variation. So this is what we just saw, and this is another copy of that. Except over here, I've changed the red Q beliefs to be 1/4, 1/4 all the way over there. So now you can see it's 2 versions of the same world, which differ by the priors. These 2 versions have differing priors, but everything else is the same. And now we can say there's this larger state space, which now has 8 states, which is an extended state space. And, I guess it's hard to see there in green, we're going to have an extended prior. And so the whole game is going to be, we're going to take an ordinary model with a state space and prior and information, and we're going to create an extended version, which has all the extended analogies and extended prior, extended events, extended information, extended everything else. And now we're going to reason in this larger model, extended model, and in that larger model now we can talk about the priors. And they aren't common knowledge. And then we can reason about the causal origins of priors in this larger extended version of the model. That's the whole trick we're going to play here. Okay? And to say that one more time with diagrams now, colors are kind of hard to see. Maybe it'll be better on the camera. So here again is a state space. we have, you can't really see it, that it's shaded according to a prior. A prior would represent some shading over this space. And we have two agents, agent 1 in red, and another agent here in green, agent 2 in
The
green.
lights go off.
I don't know if it'll help or not, but he says the
Yeah,
camera's
it'll
going
help
to
to
see.
get the
Okay.
lights off
Well,
with
please,
this.
I think
Yeah,
it's over
don't
here. Okay.
Yeah.
Agent 2 in green, and the point is, at each point state, each agent is in some information set, and what they know at that point is that they're somewhere in that set, and that's all they know. And these things are not perfectly overlapping. They're, they're disjoint in various random ways. And we can talk about that the red agent knows they're somewhere in here, and they know that the green agent knows that they're somewhere in there because the green agent is either in here or there, and they don't know which, etc. We can talk about know that they know, etc. And we can continue that iterative process all the way up to what we call common knowledge, the recursive limit of that fixed point. And for example, this whole blue outline is the common knowledge set. That is, at every point within here, they know that they know that they know, etc., that they're somewhere in there. And so any event that's in with subset of this larger set, they have common knowledge of it. And that's this key idea of a standard Bayesian model. This is just the standard model repeated here. And the key trick of this paper, this analysis, is we're just going to make copies of that. So we're going to take the same model, same information structure initially, and make copies of it. And the only thing that's going to differ here is the prior. So you can see the prior weight is up in this corner here, but up over there, or here, etc. These different versions of the model will differ in their priors, but everything else will be the same. And now we can reason about this larger space wherein they could have had different priors. That's the key point. We want to say, what could they have had different priors, and what would that be correlated with, indicate that, etc. And that's the whole point of the analysis. So that's what we're going to try to do here. And now I'm going to say it all again with mathematical notation. All right? So we have some state space. Each state is going to be an omega. It's going to be capital omega state space. We'll just assume it's finite for easy. We'll have a set of agents, n agents, labeled with an I. Each agent, I, has a prior that assigns each state to some number where, of course, they all add up to 1. That's what a probability does. And every agent is different. We can collect the vector of the priors of all of the agents into a total prior. And that's the thing that will vary across this extended model. Within a standard model, each agent at any one time will have an information set at every state. And of course, we can collect those across time, across all the people, to be the information that everybody has at any one time. We can collect those across all the times, have a total set of the whole information structure. And we have, again, this key Bayesian idea. The belief of any one agent, I, at time t, at state omega, about some event, e, which is just a subset of the space, over here, is just given by the standard conditional expectation. You take the information set of that agent at that time, at that state, you condition the event e on it, and that will give you, apply the prior to it, and that gives you their belief. And this is the standard Bayesian model. And in this model, as we've noted, this vector p is common knowledge. It is commonly known everywhere that everyone has this vector p, which is the problem.
The state space being finite is essential to Elman's result in your result?
Elman's result has been generalized quite often for non-finite results. I didn't bother here, so I can't claim to know. I can claim not to be very worried, but I don't claim to know. I would be surprised if infinite spaces made much of a difference here. But
We get
I'm
into
wrong about that.
paradoxes with, principles
Right.
of difference
And
there.
I'm just not going to claim to address those. We're focused on the issue of reasoning about the origins of priors, and for that purpose, I don't feel like the infinity of state spaces is especially relevant. It doesn't seem pressing to settle that problem, to solve this one. It could turn out they're interacting, but I don't have any particular reason to believe that, so I'm just not going to go there. So we have that model. Now we're going to extend it to make this cleverly extended model so that we can reason about the causal origins of priors. So we're going to need a space of possible priors. Each prior is an element of that space, and therefore the vector of all the priors is the element of this vector product space of those spaces. So there's a set of possible priors. Now we're going to take this original state omega and we're going to make an analogous pre-state, I call it. And we're going to just put pre in front of everything to make the extended model. So here, the key idea is we combine an ordinary state with a choice of who has which priors. So the P says who has which priors, this says the ordinary state. We combine those together to get our state in this larger extended space. And so that is in the extended space of the product of the original states and all the priors. All right, now, we're going to take any ordinary event E and we're going to extend it into the larger space. That's straightforward by just ignoring the priors. All the states have the same omega, they count as in E no matter what priors there are. That's the states as conceived of. Who cares about the priors? Just what about that? And then we can think of this event where we can think of the prior, the choice of who has which priors as an event. That is, we can take one of these, pre-states, the combination of a set of priors and a state, and we can take all of the things like that that match a particular prior combination. We just call that an event. So now we can reason about the event where they all have a certain prior, which is one of those big blocks in the previous diagram. Each of those is that kind of an event. They are basically the ordinary models within the extended model. Each of them can now be named as an event. All right? And then now we get to a key concept. We're going to have very few equations that we use, and this will be one of them. We have this idea of a prior in the ordinary space, and we can extend that into the larger space. That is, and we're going to do it conditionally. We're going to say, well, P tilde is the extended version of PI. Pi tilde is the extended version of Pi. That is, if we have a prior applied to some event, well, the extended version is just, we would condition on the subspace, which is the ordinary thing, and then we've got the conditional version. And if this agrees, then this is the extended version. So the key idea is, well, we can at least extend the prior that's within each of these ordinary spaces as a, function in this larger space, as long as we only focus on the conditional versions. Yes?
What's this pi tilde? Is that where?
It's a new name. This is the first time it's introduced. We've never seen this.
So it's being defined here?
Yes, it's being defined here.
Okay.
And the triple line is
Yeah.
in my old math traditions, the triple line meant that equality by definition.
Well, yeah, no, that's what I thought. But then you said something that said if these two agree, then something, and you're saying
Right.
you're defining it.
I'm defining it, and I'm saying this is a natural way to, as an extension into this larger space of the prior in the smaller space, right? Because we are doing as best we can. We're conditioning enough to go back to a small space, and we're forcing it to agree term by term, and then that would be the natural extension, a natural extension. Now, this doesn't fully specify this distribution. There are parts that it doesn't specify, but this seems hard to dislike this equation in the sense that you would want that to be true. If you were thinking of a extension of this into larger space, this is something you would want to be true about. And finally, we can take any one agent's information and we can just project it in larger space, just as you would do with states. Again, in this case, you know what prior you have, and you know what you knew. And so now you know both what you would have known plus you know your prior. And that's what you typically know in an ordinary time t in this model. So in this larger model, at this point, we're still sticking with agents who still have priors as common knowledge. For all t times t where this equation is true, the priors, they do remain common knowledge here. But that won't be true for all times. Okay, so in this extended world, now I'm going to allow a new set of information sets that are information in this extended world, and they will agree with the other ones at times t, but not at other times s outside of t. So this is the key. I will have times t where all the standard things are true, even in the extended model. But now I'm going to allow times s, extended times, before the times t that are in the model, an uber, ancient time, abstractly imagined before the previous model exists, when the assumptions of the ordinary model no longer need to be true. So again, for t in the intersection here, they're agreeing, but not necessarily at other times. Now I'm going to introduce a prior over this larger state space. And I'm going to let each agent have a different pre-prior. And I have not constrained it very much. That's the key point to note. I will constrain it through a very small, very limited number of ways. But in general, at this point, they can have a pre-prior that's completely unrelated to their prior. there's this larger space, and they have a prior over that space, and they have over each subspace, they have a prior there, and so far these are as yet unrelated. And we will ask what relations are appropriate. And of course, in particular, they are allowed to have uncommon priors. These pre-priors can be different. There is no requirement that they be the same. But now we are going to make a key assumption to relate them. In the last equation we had that mattered, we had this p tilde by, which was the projection of their prior into this larger space. And now I'm going to say, when they have their pre-prior and they condition it on knowing what their prior is and what everybody else's prior is, then it agrees. So now you have this idea, they have this pre-prior, they update on learning what their and everybody's priors is, and then at that point, they have their ordinary prior. So there's a connection now between the pre-prior and the prior, which is this equation demands that the prior be the natural updating of the pre-prior on learning the fact that they have a particular prior, that everybody has the prior. And that's a key connection between this extended space and this more traditional standard space.
So when I first saw p tilde, I was thinking that was the pre-prior. So if q is the pre-prior, then can you remind me again what p tilde is?
Sure. P tilde was just the natural projection of the prior into the larger space.
Okay.
So we have again, the whole game here is we have a standard model with a standard space. We're extending it into this larger space. In this larger space has all of the analogous things, but now we have to start making connections between the things in the standard space and the things in the extended space. The question is, what are the relationships? So this is a thing that's expressed in terms of the larger space, but it's still defined primarily here as a projection of the thing in the standard space into the larger space. It's a natural, it's a structure available to be in this next equation of this being equal to that. Because this is in the extended space, and that's in the extended space, and now they can be equal there. Basically you're saying, we're going to assume that your pre-prior, is something you start with, and then you update on learning what your prior and everybody else's prior is, which then puts your information down within a standard space, and then and then you now have your prior in that standard space. So the pre-prior is, in essence, the natural pre of not knowing what your prior is. And so the pre-prior is the thing you can now use to reason about the causal origins of your prior, because your pre-prior doesn't assume it knows what your prior is. It allows the possibility you have many different priors. But then at some point you learn what your prior is, and it needs to also be consistent with what you then believe once you learn what your prior is, that's your prior, and then that's what you believe. Yes?
Why do you insist that once the person learns the priors of all the other people as opposed to just the prior of the person herself?
Just because in a standard model, all the priors are common knowledge.
I see.
So it's just the moving from the extended model to the standard model. Because in the standard model, not only do you know your prior, you know everybody's prior, then that's what I need to have you learn in order to now be in the standard model, which is where you have your prior. If you only learned your prior, not other people's prior, you're not yet in the standard model. Because in the standard model, you know not only your prior, you know everybody's prior. So that's what I need you to learn so that I can put you now into a standard model. Okay, and so now again to notice, in this model, P is common knowledge at times in the T set, the times that match the standard model set, but not necessarily common knowledge in these other extra times we've added. And that's the whole reason we added this structure. The whole reason we went for all of this is to be able to have a structure where the P is not common knowledge, so that we can now reason about it with probabilities. And that's the whole game here. So now we have that, we're almost home. So we have these two equations that we trivially combine, right? A equals B, B equals C, A equals C. But we have to now look at this final equation, and we're going to expand it out again. So this equation here, this P vector, can be also written as this expanded version. This is the P that includes all the components, and so I've just expanded out those components here, right? P1, P2, all the way up Pi, Pn. So this is the equation we've produced here. Again, just to walk through it. When you start out with your pre-prior, and you're thinking about any event E in the larger space, what happens after you learn what your prior and everybody else's prior is? Well, now you've moved into the standard model, and in that standard model, you have your ordinary prior about that event E, and that number is the same. That's the key point, right? Well, that's in a sense this equation rewritten here again. But now I want you to reflect and notice some key definitions of conditional independence, right? According to some probability distribution, we say that A is independent of B given C if P of A given B and C is the same as P of A given C after we drop B. That's the key concept of conditional independence, right? And this form I've just written is of this form. That's the key thing to notice. That is, all these other P's dropped. They don't show up over here. They were in here, not there. Therefore, we can draw claims about the conditional independent structure of my prior probability distribution Q. And everything rides on that. That's my whole result. A reasonable person, yes, go ahead.
You've added an extra condition here, B tilde.
Where?
Is that
That's without loss of generality.
that follows?
I mean,
Okay.
you can take
Okay, if
any
that's
probability equation and condition both sides on something that has a non-zero probability, and the equation is still true. So.
Yeah, but in this, I'm not.
I shouldn't actually have those in these. It's just distracting at this point. So
Well, we agree on that.
and so I think the paper. I'm not sure whether it was here at the right point, but yes. The general argument is you can take any probability equation and condition both sides on the same thing, and it's still true.
So yeah, I agree on that. Except I guess my understanding was that you haven't really specified QI except up to these conditions that you require it to satisfy, and it's not fully specified by that. There is no such measure, right?
Oh, I definitely have not specified all of the elements of Q. I have said there is a Q, and I've noted some constraints on it. I've not given a formula for creating a Q. In fact, that's part of the point. The idea is to say, have whatever Q you want. As long as it satisfies the following conditions, then I'm going to get the following results. So, imagine you're making a weird Q as best you want. I'm still going to get certain results. And so the key point is this basic equation representing the pre-prior and what happens when you update on learning your and other people's priors satisfies key conditional independent structure. And that can be represented by these two theorems, for example, here. Any event E is independent of any other prior given my prior. And any event E depends on my prior only via this equation. So my prior and any event E are informative about each other, but given my prior, no other prior is informative about any other event E, nor is E informative about any other prior. The information structure has my prior screening off all the other priors to any event. Events informative about my prior informative about events, other people's priors uninformative about anything except via my prior. That's special. That makes me special in this structure. So, corollaries. If you talk about my prior, an event conditional on my having one particular prior, and it happens to be equal to somebody else's prior, then those priors assign the same value to the event. If we swap my prior and your prior, and we still get the same number, then we have the same priors. If an event is just as likely in situations where my prior is switched to somebody else's, those two priors assign the same chance to the event, i.e. These are conditions of symmetry, and they say symmetry implies equality. The symmetry of these, again, we have this key asymmetric conditional independence structure. If we require symmetry, the only way to produce that is by identity. They are the same priors, in which case they no longer need to screen off each other. Right? That's the easy way in which other people's priors can be informed about the world. Only via my priors, they are the same as my prior. Otherwise, there's no other way to do it. So, tale of two astronomers. So, say they disagree about the universe being open or closed, And they think this is due to their priors. They're trying to justify this by their priors. So they have to believe the following things. Nature could not have been just as likely to have switched our priors if both the universe was open or closed. And if the universe was one way, there has to be one set of processes to switch our priors, and then a different set of processes that switch priors if the universe is closed. Welcome. And of course, if I had had a different prior, then it would have been in the situation where the chances of these things were different, but given my prior, the fact that he has a different prior says nothing useful about anything. There's another way of restating this. Okay. Again, say the usual, if these were encoded in DNA according to the usual genetic rules, these would just be false. These are just not at all plausible ways that you could produce different genetic patterns based on the universe being open and closed. As we usually believe, the universe being open and closed does not influence which child of parents have which set of genes. That process is just not influencing that.
It could, or there are processes for which that could be the case.
I mean, if there are, then yes. So, but the vast majority of
Yeah, I agree. In this case, it would be bizarre if it were, but
well, the vast majority of other events in the universe are also not correlated with which children gets particular genes in a family. That is, our standard models of genetic inheritance have the random process by which some kids get some genes and others get other genes being almost entirely independent of most of the rest of the universe outside that very small biological process.
But your priors might form in other ways. For example, from your parents, and who your parents are might make a difference in what your priors are.
Sure, I was focused on the difference between two siblings, say. So the difference between two siblings is mostly explained by random events in,
Well, might be
within that parent. The common factors of these
parents.
parents.
Parents are undergoing different things at different times when the siblings were born, and that may make a difference.
It could, right? But so the key.
But you're assuming that that's not the case here, right? So
this is a more particular example, but the general principle for which we have this general theorem here is pretty strong and not very dependent on these many particular circumstances. So again, the key point to summarize, and because I'm basically done, we can open up for discussion. We take a standard Bayesian model. In a standard Bayesian model, priors are common knowledge. We want to reason about the causal origins of priors. We have beliefs about which combinations of who has which priors are how plausible. In order to reason about that, we need a framework in which priors are not common knowledge. We therefore take a standard model embedded within an extended model, and then we make the mappings as necessary so that the parameters are the same, and then we have a pre-prior in the larger space, and at some times that pre-prior, it does not be common knowledge, whatever these priors are, and then within that pre-prior, we can reason about the causal origins of priors, and then one key rationality constraint, which is driving everything, is to say, your prior should be what your pre-prior would say you should believe if it conditioned on the fact that you and other people were assigned particular priors which put you within a standard model. So you start in the extended model, you learn which standard model you're in, and then you have the standard beliefs according to the standard model, which is your prior. And so that key relationship, we notice it satisfies the conditional independence assumptions, which say that your beliefs about the relationship between your prior and real events say there are connections, and other people's priors are not connected except via your prior, which makes your prior special. So either you believe you are special with respect to the universe in terms of how your prior was produced, in terms of correlating with things, or your prior is common. You have the same priors. And so, unless asymmetric causal origins are plausible, common priors are therefore argued for, and therefore this is an argument for the rationality of common priors for Bayesian agents, who do not believe they have special asymmetric processes that produce the prior. Ta-da, QED. And that's that. We might want to put the light on so that more people could feel comfortable talking to each other. And so, it's a short proof. There's a lot of structure in terms of defining concepts and setting up definitions and things like that, which should be relatively general. The proof is really short, the constructions are really proof, and it seems the conclusion is grand, because people have been arguing about common priors and their reasonableness for a long time, and struggling to find rationales why we should have common priors. Other people have just said, well, our differences should be explained by differences in beliefs, and yeah, that's plausible, but doesn't seem overwhelmingly persuasive. Why couldn't we have different beliefs, even if we had the same information? One might say. And this says, well, if you have beliefs about their origins, not so much.
So, I mean, I definitely follow the theorem, but it's not clear to me right now. So here's another possibility I could imagine. What if I think that my prior is independent of actual events, but I think your prior is anti-correlated with actual events? Does that, would that be a counterexample to this theorem, or is it actually okay with
Well,
this theorem?
if you are not satisfying this equation, if that's true,
Okay.
right? Then now, you are not, if you think your prior is independent of events, you should not embrace that prior. If you have a choice, you should pick a prior which is the average over the priors you might have, right?
Right.
What sense does it make to pick a particular prior that was just randomly assigned to you?
Right.
That doesn't seem epistemically confidence-inducing. I mean, you know.
For an what they call an objective Bayesian, there's a logically correct prior.
Yeah.
That person will think that his prior, if he thinks that that's his, he'll think it's special.
Well, of course, usually objectively correct priors are common priors because there's usually only one objectively correct prior. So that already gives you the conclusion easy. So I was.
Yeah, but it might not be in common. There might be other people who don't have.
Well, then they have the incorrect prior.
And the incorrect prior.
Right. So.
Right. So you're thinking you're special.
So they can't know that yours is the objectively correct one. Your knowing that your one's objectively correct has to be something they don't know, something they don't have access to.
So what's the relationship between, if there is one, between this result and objective Bayesianism? I mean, the feeling I had as you were going through it is that it gives some
So,
support.
I mean, objective Bayesianism is usually on the basis of arguments that anybody could see. It's not, if you had a private data set that was producing your objective Bayesian, that isn't really a prior, right? That's posterior. So if the objective prior is because of objective reasons that everybody can see, not based on information, then everybody else would know they were objective too, in which case
Except
they'd
that
become.
those people who are objective Bayesians who present them as being based on things that everybody can see, usually many people don't see it, they don't agree with it.
Right, so obviously one simple way to model agents who are not Bayesian is you have Bayesian plus error. So once we introduce the space of agents who have Bayesian plus error, we could of course believe that I am reasonable and the other people have error, right? But, you know, they won't believe they have error. But still, that's one way to believe I'm special, of course, right? Is that I have the true insight into the correct prior and other people don't, right? But that again requires us to model reasoning over logical certainties, which the Bayesian framework is usually set up not to do that, although as I mentioned, you can actually reason about impossible worlds, and in which case we end up with the question, why don't we end up agreeing? As I said at the beginning, a lot of this for me is motivated by the agreeing to disagree literature, rationality of disagreement, in which case you might say, look, if agents with common priors won't disagree, how will they disagree about what the objective prior is exactly? You know, they all have the same reasons available to them. They hear somebody else disagree, won't they agree on that? In which case, you know, it looks like we're stuck with agreement as the thing that rational people should do. Which again, does seem to be right. So, in case you care, I have these two books out lately I'm happy to pass around. But the first book, the most recent, The Elephant in the Brain, is a book about how we have hidden motives and how we aren't very honest about what we do. And my basic answer to the question of why do people disagree is they are not actually trying to be accurate as their first priority. And so that's why, in fact, although Bayesians would not disagree, people do. And you know, that's why I, in a sense, left the agreeing to disagree philosophy literature once I realized that that was my best explanation, because I realized, well, analyzing in more detail exactly what a rational agent would do is somewhat beside the point. The reason why people disagree isn't these reasons, it's something else, but I still have a soft spot in my heart for, you know, wondering whether other people are persuaded by this and whether I can persuade other people.
What's this a picture of? Is that a Russian?
It's intended to be similar to that and to look like an elephant, of course, both. So that's the clever image that I didn't invent, but somebody did.
The moral isn't to feed your brain peanuts.
No, it's just that there's a hidden elephant in your brain, and the Rorschach test is an image of something hidden in your brain, and so making it look like an elephant gives the metaphorical idea that there's something hidden in your brain.
This implication again is this doesn't seem obvious to me. Is this, I mean,
Which one?
the 1 and 2 implies this
Well, that's just right here.
that's 1 and 2, yeah.
These are 1 and 2, and this is the implication. So we're just saying this equals that, this equals that. You see these two are the same, so we're basically saying this equals that. And then we're expanding out P there.
Yes, sure.
That's it. That's all there is to it. So this and this are the same. That must be the thing that's not clear here. See, the only difference between this and this is
This
that I
slide is
expand P out.
clear. This slide is clear, but you've added a B in the other slide, so you're
So
talking.
that's the thing I took back later, saying if you don't like that, then forget about it.
No, so if nothing that you said actually seems to depend on this in this slide, but I wonder what, you do have it in the paper, so it seems that you are making,
As I said, I thought I was being more general
oh, I see.
by noticing that any probability statement that's true is also true when you condition both sides on the same thing. So it's a more general looking result to have it be conditioned on something.
No, I don't believe this is true.
And why not?
I mean, I just don't, you haven't defined a probability measure on the previous slide. You've defined a condition that is satisfied for a specific condition, which is the condition conditioned on P1 up through Pn. You haven't defined what Qi is, so it's possible, I'm,
So can't Qi just be a probability measure at this point in the analysis? We say for any probability measure Qi, we require this equation. I mean, do I?
unless I'm doing a very simple calculation wrong. It would seem that if this is true, then Q has to be actually, that Q has to actually be defined as a function of P.
Again, the definition was this was just the pre-prior. We talked about, just as with priors, we have a pre-prior. It's a prior over the whole space. We gave our notation for it. We collected them, and then we gave a constraint on it. It's just, we introduced it here as the pre-prior. Just as we have priors, we have pre-priors over the extended space, and that's the pre-prior. We name it, and then we go on from there. So at this point, it's a probability distribution because it's the prior over this larger space. If we're allowed to have priors over the regular space, we're allowed to have a prior over this extended space because the extended space has all the structural properties of an ordinary space.
Harry, are you thinking that you can have Qi that satisfies the not defining like the structural equation, but somehow there is a B's and B tilde such that the ladder equation on the other side doesn't hold?
Yeah.
Rephrase?
Sorry. I think what Harry was getting at is, can we turn to the next slide?
Yes.
Yeah. So this is the only feature that we want Qi to satisfy. Probably that we want Qi to satisfy.
This is what we'll focus on to draw our conclusions.
And I think Harry was saying, you can have a measure Qi that satisfies this equation, but doesn't satisfy the next equation you have on the next slide. Namely, you have a B. Sorry, turn to the next slide, and then Harry's wondering whether or not we can have a B and B tilde, such that whatever measure we had from the previous slides that satisfy that equation does not satisfy this latter equation. Therefore, the implication doesn't hold.
So,
And Qi is a probability distribution?
I
yes,
think that was the worry.
over the extended
Well,
space.
I'm not producing a counterexample, but I'm saying that there's it's not obvious that this must be satisfied by any measure that satisfies the previous measure.
Well, so
Including if the measure is a probability distribution? Like assuming, so not just any measure, but Qi is a probability distribution?
Assuming Qi is a probability distribution satisfying this.
then can I condition both sides of a probability distribution equation and get the equation?
Yeah, but to assume that you can condition on anything and it remains equal is already assuming something about, it's assuming more about those the relationship of those measures. Right? I mean, I can have two probability measures, P and Q. P of A given B equals Q of A given B. That doesn't mean that P of A given B and C equals Q of A given B and C.
Right.
Right? That's all I'm saying.
Right.
So, this here, say without the B's,
It's fine.
this is a distribution over in essence, over the whole state space omegas, right? I mean, I'm talking about in terms of ease, but basically, once I've conditioned on knowing what everybody's priors is, I've projected down to one ordinary space. And then in that ordinary space, this conditional probability has all the exact structure of the PI. It's exactly state by state, number by number, exactly the same as that distribution. So conditional versions of it should also have the same structure, I would think. But the key thing is, this is not, B tilde is not any possible event in the larger space. It only is a sensible projection of the things in the smaller space. That may be the thing that's...
B tilde equals the omegas that are in B and also all P's, overall possible
So again,
P's,
the
right?
definition of an extended event here
Yeah.
is where we just don't care what the thing is. And so we're basically summing up over all of the other things, but when we condition on a particular P, it's basically the same set.
I think what you wanted is not so that conditional on B, that the conditional measures are the same, but rather you wanted B tilde to be the index, such that when you index Qi by B tilde, that it generates this conditional, this measure, as if what P would generate on the space.
I agree that it is, but it seems to me it would be the same number, but maybe I'm missing
So I
something.
think what you wanted is not only such a, the conditional marginal, that's a weird word, the conditional marginal match, but also the conditional also match, which is actually on the conditional joint space, that everything matches. So it's,
But in this case, that would be true for a general thing, but this is a very particular kind of event. This is where we take an event that makes sense in the smaller space and we project it into the larger space. So it's much less general than you might think it needs to be. But in any case, for the purposes of everything I've been saying here, I don't need it. So I'm not sure
I agree.
why it matters. I mean, unless you want to say, these are true in the aggregate, but as soon as we start conditioning on something, these are no longer true.
Well, supposing that, I mean, it would seem to limit the scope of the conclusions, because what you're saying then is, if we, it seems that what you're saying is that about this agreeing to disagree aspect, that if we might have common knowledge of all of our priors, but then we also have knowledge of an event. But once we observe an event, that we somehow, that would break the whole symmetry and mean that we don't have to agree on their probabilities conditional on that event.
If arbitrary events could break these things, but I just can't see how they could. I don't see how these equations would no longer be true when you condition on something. When you condition on things within the smaller ordinary space. I agree that if you condition on arbitrary events in the larger space, that would be true. So here I'm restricting myself to conditioning on these smaller space events. So these are only conditioning on things within one standard model. That's the only kind of things we're conditioning on here, not arbitrary other events. But
So you have outlined a little bit at the beginning about how there's been this general progression of generalizing this.
of the disagreement results, yes.
Yeah. I mean, it's still, obviously, like, it's quite difficult to, like, you know, cross the T's and dot the I's and get everything working, but, I mean, it still seems like it's rather simple in terms of, like, you know, is there any hope to get some kind of, you know, some kind of generalization with, like, you know, a process instead of a single step, like, and with error as well?
I haven't tried.
Okay.
So the context here is, I actually published this in 2006.
Right.
And, you know, deafening silence. And then I was invited to give a talk at, you know, Rutgers probability seminar, and I said, then maybe those people should hear about this, because nobody, I looked quickly over the literature on common priors. I don't see much of an advance since I published this in 2006, and I said, I still think the literature doesn't get that there are ways to give arguments for common priors. If you look at the literature for arguments for common priors, it's really thin. There's really not much there, basically. There are characterizations of the equivalence of common priors and other things. Like if there's ever an event you might bet on, even if it's the same payoffs, then that's equivalent to having uncommon priors. That was a theorem proved like that. You can prove theorems about, belief hierarchies and common priors when they're the same, but again, as a normative point, should you have common priors, I just haven't seen much of it. So I thought this is a argument for normatively for common priors, and since so many people argue about priors for so long, that this would be a big deal. So I decided to. But of course, in general, one waits for interest before one pursues elaborations of things. You do first steps, and whatever people seem to be more interested in, pay more attention to, you kind of do second steps on, and things you do first step and people don't care much, you don't tend to follow as much. That's the case here. So, but I thought, given this opportunity to come talk, I would tell you about the argument for common priors. I also mentioned in this slide, of course, that there's this other way to think about disagreement. So as I said before, but some of you weren't there, so again, so I'll repeat. The literature on the rationality of disagreement in philosophy has been taken as its prototypical situation. Two epistemic peers who at the same time estimate the same thing, discover at the same time that they disagree, and then are asked whether they want to move toward the middle. I find that actually a pretty problematic scenario to get many results from. A much more productive scenario, I think, is to imagine two agents, one of whom estimates something for themselves, and also at that time estimates what somebody else will later estimate, and estimates the difference between those two, and merely reports the sign of that difference to the other person. So report common knowledge or common belief of the sign of the difference, I can prove, produces that they don't disagree. And that avoids many of the problems of the other formulation, because of course the other formulation has these two experts, one of whom could actually know something the other one doesn't, and might actually know that, and that could be reasonable. Whereas in this formulation, even in a situation like that, the sign they produced would inform the other person of that, and a reasonable person would respond, and that breaks the possibility of disagreement.
Is this a correct moral from what you're saying? If there were a group of perfectly rational people, then they ought to have the same beliefs.
Same priors, yes.
Same priors, and if they shared information, they would have the same.
And they would therefore not knowingly disagree under very limited sharing of disagreement signals.
So one explanation of that would be if they were objective Bayesians, right? I mean, why would they be like that? I'm looking to see whether this argument that you're giving might be an argument for objective Bayesians.
Well, you might be able to just prove an argument that says the only way to have common priors is to have a common source for your prior.
Right, so that's a good way to put it. So
But a common source could be the Uber Adam and Eve. They had a prior and we've all decided to keep it. That's a way to keep common priors.
Right,
So,
but if you think this is supposed to be rational, then you want to get some.
I mean, I think of rationality as collecting rationality constraints, slowly, iteratively, one by one. The more rationality constraints we have, the smaller the space of things we'll call rational. And eventually the question is it unique or not? We don't have to know that at any one step. We just have to look at any one constraint and say it's not a reasonable constraint.
So I was wondering whether or not somebody who was an objective Bayesian, I have a friend from a long time ago who's a well-known objective Bayesian, and whether seeing your result, he should jump up and down and say, yeah.
Well, if he
thought, agree with your result,
if he thought it was going to be incoherent to not have common priors, then he might think, and I know why.
Right, that's right. So
he might think that this result supported his, but from a different basics. But as an objective Bayesian, he must think he has a different argument for why we should have common priors. That is, he thinks he knows what those priors are, they're unique, and there's a unique argument for why you should have them.
Well,
that's not what I'm arguing.
But he could give you, wouldn't your argument support his view by the reasoning that you just gave? His argument would be, well, I've heard an argument that you should have common priors. And the best explanation, the best account of having common priors is being an objective Bayesian.
I don't know what an objective Bayesian exactly claims is the objective basis. So I've shown they are common, but It could be the source of commonality isn't what would count for him as an objective thing, so I don't know what is strong enough to be objective from that person's point of view. But if,
Well, you've shown it's intersubjective, so at least among the people who are common knowledge assumption is holding. So it's intersubjective. Usually the good explanation for why there's wide agreement is that there's a fact about which people are agreeing.
so just remember, I took one person's pre-prior and made assumptions about that one person's beliefs about their own future beliefs and others. I did not invoke more than one person. I only invoked one person's pre-prior beliefs. So in that sense, it's not intersubjective. It's one person's belief about several people, not several people's belief about several people.
Right.
And that was enough. One person's belief.
Just two quick clarifications. First, I was wondering, you said in the standard model, in the priors are common knowledge.
Yes.
So I was wondering whether or not you can relax that assumption and still get some kind of a result, or is that, I feel like that's
The whole point of the structure was to find a way in which I could relax it. This is the only way I figured out how to relax that assumption. I don't know of another way. If you know another way, great, but show me. I can't think of another way to relax the assumption than what I've just done.
Okay, I mean, the reason why I feel like you haven't relaxed it enough because once you project it down to the particular
yeah.
model, then you still assume that when you condition on, that's why you're not conditioning on PI, you're conditioning on P in total, because once you project,
yes.
you want to get the person to believe everybody else by it.
Right.
Um,
But
yeah.
the structure of the standard model itself just doesn't seem to have any way for the priors not to be common knowledge. There isn't a hook in there. I can't think of a way to do it. So all I could think of doing was embedding the standard model where it's common knowledge within a larger standard model where that model's priors are common knowledge, but that model's beliefs about the submodel are not common knowledge, and then I could reason at that larger level about the priors. If you can think of one, great. I mean, happy to toss this if you can find a way to do it more directly, but I couldn't think of one.
Could I suggest something?
Sure.
On this line? So my understanding of what you're trying to provide as a basis for reconciliation is to embed essentially into a hierarchical. Essentially, you're hierarchalize the argument between two agents. That's kind of how
I'm embedding a model in a larger model with the same
Right.
structure. That's a common reasoning trick.
Using two or more agents' beliefs and construct upper and lower probabilities and use that as the ground of priors to work with. The reason why I suggest this is because Barry was saying that, if you're a Bayesian, you insist that only one specific prior could encode your belief about a state of matter.
So if I recall, upper and lower probabilities would just be produced by two different priors. One includes the lower one.
No, they
It's a
could
set.
be, it's a set of probabilities and they can be.
Right, probability set.
It's a set of probabilities that could be
Yes.
invoked by an arbitrary collection.
But that set is common knowledge.
Yes, well.
That's the problem. That set is common knowledge. So
But-
I can't reason about that set and its causal origins when it's common knowledge. That's my problem. So I could embed that in a larger thing with
That is not to say that each agent would have to believe in them.
They would have to be common knowledge what each agent's sets were. Which means I can't have probability reasoning about the origins of those sets.
I'm not sure if that distinction is, well, okay, so the reason why I bring it up is because, well, what Barry was saying is that in the Bayesian argument, people take, problem with the fact that you have to claim this unique prior as your representation of state of knowledge, whereas sets of probabilities could give you this flexibility in encoding even vacuous information, in which case you would just have the entirety of all probabilities.
So you replace one prior with a set of priors,
Yes.
but you retain the fact that that thing is common knowledge.
But to say that you have all the probability measures as a common knowledge is as if you said nothing. So there's a degree of the specificity of the common knowledge when you invoke the set, because there's a sense of the size of the set or how specific the set is.
The analogous work, I can just see the analogous structure will be, I'll end up saying that the my set is special. My set is correlated with other events. Other people's sets are not correlated with events except via my set. That's how it'll have to work out. And that's what I would prove with this extended version of the sets. And the fact that it's a set isn't doing that much work there, except it's allowing a more general representation of beliefs. But I'll still need to talk about those sets. Now, of course, the pre-prior, I'm using these conditional independence assumptions because the prior, if I have a set of pre-priors, I'm not sure what I'm going to do with that exactly. But if you can come up with something great, I mean, I'm sure this can be generalized in many ways, and I haven't tried that far, but that's questions which generalizations are interesting.
Yeah, so this does seem to leave it open. If we take your pure rationality constraints, that two agents could just have uncommon priors, both think that they're special, and both be rational.
My argument is depending on a priori implausibility of asymmetric prior origins. If you're willing to bite that bullet, then
Right.
you can maintain uncommon priors here. You just have to accept asymmetric origins.
Right.
And they'll need to each believe asymmetrically in their asymmetric origins, right?
Right.
I didn't say that as explicitly. It's not enough for their origins to be asymmetric. They will each need to be special in the way that they can't allow others to be special.
Right.
They can't all be special. Each
Right.
of them has to believe they are uniquely special in the way that the others can't be. They could each believe that separately. They, of course, can't agree.
Right.
on those
Well, they
questions.
might belong to tribes.
Well, then within each tribe, they would have to agree.
Yeah.
And across the tribes, they would
That sounds,
disagree.
that's not unrealistic. Real.
No, but normatively, it might be less believable. Because we might say, you're part of this tribe, where did your priors come from in this tribe? Well, tell me about the causal origins of the priors of your tribe, or the prior set for your tribe, and explain to me the theories of culture or genetics such that it produced this correlation between your priors
The
and events.
explanation might be theological in both sides.
Yes, that would be the sort of desperate means one would have to resort to. I will reject the usual theories of culture and genetics in order to invoke my God having intervened to produce our group being special. Yes, you could try that.
Well, let me put it another way. If we have uncommon priors, it doesn't require me to think that you're irrational. It just requires me to think that my prior is special.
So in this framework, everybody is assumed to have a prior. So we're not allowing irrationality of the form of not being a Bayesian.
Sure. Right.
But we are open to what the priors are and what we believe about them. And so in fact, each person believes that if somebody else has a prior, that's a bad prior.
Right.
And not a good prior. And so they are.
But they still might, he's saying they might be rational because their changes in belief are always rational.
Well, again, the general concept of rationality is just how many constraints can we add and how far do we get? And so this is a constraint. And that's the proposal here. I've got a new constraint you haven't heard of before. You haven't heard of very many constraints, so hey, this should be a big deal. That's the intuition.
Sorry, this is changing gears.
Sure.
I was just wondering, so first you mentioned knowingly disagree, and I was wondering whether or not that's different from disagreement. So it seems like
Yes,
here
it
we're
is.
talking about only knowing disagreement. And so presumably these two come apart.
I mean, so that is the key point of the slide. This slide was to summarize the state of the literature on agreeing to disagree from the economics point of view. It's completely obvious that two people could acquire differing information and produce different beliefs that way. So, if you walked into this room and thought there was a mouse in that corner, and somebody else walks in the room and they think there's a mouse in this corner because they saw different lighting and different sounds, there's nothing strange at all about that, right? You could have started with exactly the same priors, you get different information, you have different beliefs. Overwhelmingly obvious and straightforward. The puzzle is when one person talks to the other and say, I saw a mouse in that corner, and the other person says, no, I saw it in that corner. They each have heard that the other person disagrees. Now, what happens then? That's the knowing disagreement. Can they knowingly disagree? Can they disagree and know they disagree with somebody else? That's the puzzle. That's the thing that's problematic. And in fact, for this particular form of disagreement, it in fact can't exist. That is, no matter what's happened, and just for the moment, if I think, what's my chance the mouse was in this corner? And I think, you're going to say in a minute what you think the chance is, and I'm going to estimate what you're going to say, and now I'm going to look at the difference between I'm saying now what I think you're going to say, and then I'm going to tell you the sign of that difference. That's all it takes to make the disagreement go away. Only sign I can tell you is 0, that's the key point. If I'm going to tell you the sign between what I think and what I think you'll think, the sign has to be 0. I can't tell you a direction in which you disagree. That's a, I can't know which way you'll disagree.